Thanks to the chair, and my name is Jiaheng Zhang. I'm a PhD student at UC Berkeley. And today, I'm happy to be here to talk about our recent work on polynomial commitment with a one-to-many prover and applications. It is a joint work with Tiancheng, Thang, Hoang, Elaine, and Yupeng, Zhang. So first of all, let's talk about the background on zero-knowledge proofs. Zero-knowledge proofs is a cryptographic tool between two parties. The first party is the prover, and the second party is the verifier. And in the protocol, the prover wants to convince the verifier some computation on function C with input x and w equals y. Here, x is a public input, so x is known to both parties. W is private to the prover, and the verifier doesn't know w. After seeing the output and the proof, the verifier can decide to accept the statement or reject the statement. And there are three important properties of zero-knowledge proofs. The first one is the completeness. It means if the prover is honest, the statement is correct, then the verifier will accept it. And someness means if the prover is cheating and the statement is incorrect, the verifier will reject the statement except for negligible probability. And zero knowledge means the proof doesn't leak any information about the private input of the prover. And there are many applications of zero-knowledge proofs. For example, we can use zero-knowledge proofs to create anonymous payment on blockchain. Also, we can use the zero-knowledge proofs to build the zk-ROP protocol, which can be treated as a solution, as one solution for the blockchain scalability. And in most of the ZKP protocols, they just model the function C using a circuit. So as you can see here, the x and w is still the input of the circuit, and y is output of the circuit C. So in the traditional setting of the zero-knowledge proofs, there is only one prover and only one verifier. But in our work, we consider a new setting with one prover and n verifiers, and we call it one-to-many prover. So as you can see here, the input is still x and w, and the circuit C remains the same. But the output y can be divided into n pieces, and each verifier will only get one component of the output yi, and each verifier doesn't know other components. So that is our new setting, and why are we interested in this setting? Because it has some applications. For example, a direct application of this new setting is a verifiable secret sharing. So in the verifiable secret sharing scheme, we have one prover and n verifiers. And the prover owns the secret S key, and he wants to share the S key to n verifiers. So the n verifiers can help him to keep the secret. So he splits the S key into n pieces and sends these n pieces to each verifiers along with proof. And then if all verifiers get together, then they can reconstruct the secret key. Here is the threshold T in the scheme. That means any subset of verifiers with size at least T, they can recover the secret key. However, any subset of verifiers with size smaller than T, they can learn nothing about the secret. And we suppose T has the same order as N in general. And VSS has also some applications in the real world. For example, it can be used in the MPC protocol, and it can be used for the cryptocurrency wallet, so it can help the user to keep their secret key. And the VSS can also be used to construct distributed key generation and the random beacon. And the classic secret sharing scheme is the Shamir secret sharing. So in the Shamir secret sharing, the prover encodes the secret key with a polynomial f, as you can see here. And then he evaluates f on n different points from 1 to n. Then he sends all these evaluations to n verifiers respectively. Then the verifier can recover the polynomial, the secret by polynomial interpolation. okay, since the one-to-many prover setting has some applications, so we want to have like a new and good algorithm for this new setting. And the naive solution is straightforward. So in this case, the prover just runs the circuit n times for n different output. So it will generate n different proofs and send all of these things to the verifiers respectively. And then it calls the prover in time n times c, because it runs the circuit by n times, which is not good. So we ask a natural question: can the prover reduce all n proofs for the cost of only running the circuit once? And the answer is yes. So in our new algorithm, the prover can run the ZKP protocol on the circuit C only once to generate the n proofs in one shot. So the prover time will be reduced to linear in the circuit size, which is also optimal because the prover at least needs to run the circuit to get all of the output. And next, let us move into the technical part. So in this part, we just suppose the circuit C is layered. And there are many ZKP protocols like Herax, Libra, and Virgo working on the layered circuit. And in these ZKP protocols, the general idea is that they can reduce the claim about output to the claim of the input layer by layer. So in the layered circuit model, our general idea is in the first step, we insert one extra layer on top of the output layer. As you can see in this figure, we insert one layer YR on top of the output, all of the output Y. And you can imagine YR is just random linear combinations of this Y. And then the prover runs n protocols with n verifiers, and then he can reduce all of these n claims about different YI to the same claim about YR. So the prover aggregates n claims in one layer in one step. And the prover time for this step is only n log n. And the next step, n verifier will share the same claim about YR. And then the prover can run the GKR protocol, run the ZKP protocol to reduce the same claim about YR to the claim of the input. And all verifiers should share the same proof. So the prover only needs to run the circuit once. The cost of the prover is linear in the circuit size. And by combining these two steps, the final prover time is still linear in the circuit size. And in our algorithms, there is assumption that all verifiers have the same randomness. But that is not true in the non-interactive model. So in our paper, we also propose a new Shamir transformation to force all verifiers to agree on the same random challenge. I don't have time to talk about this, the details, but you can check our paper for more details. And then we will have the new one-to-many prover algorithm. We can apply our techniques to the Shamir secret sharing. So in the Shamir secret sharing, the input is the encoding polynomial f, which is private to the prover. And the circuit is just the FFT circuit to get n evaluations. So in this case, our prover time is only n log n because the size of the FFT circuit is n log n. But the naive solution is n squared. So we reduce the prover time from n squared to n log n. And we can build a VSS without trusted setup if we apply the transparent ZKP protocols like Herax or Virgo on the circuit. And that is the experimental result on our VSS without trusted setup. And the black square represents our solution, and the blue one represents the naive solution. So as you can see, our solution is much, much faster than the naive solution. And the naive solution cannot scale up to the large instances. And as the number of parties increases, the gap becomes bigger. And additionally, we also have the contribution on optimal VSS scheme based on the KZG. And the KZG needs a trusted setup. So in the original VSS scheme using KZG commitment, the prover computation is n squared, and the proof size per verifier is constant. And later on, in the following work of in Elaine and their co-authors, they improve the prover computation to n log n, but it brings the overhead of log n for the proof size per verifier. And in our work, we aggregate these two results all together, so we can have an optimal VSS scheme based on KZG, which has constant proof size as well as n log n prover computation at the same time. And I don't have time to get into the details. You can check the paper for more details. And I'd mention here the same algorithm was also proposed independently by other researchers. If you are interested, you can check via the GitHub link. And finally, that is the summary of our work. So in the first part, we have a new one-to-many prover setting, and we have a new algorithm for this setting. And applying the same techniques to VSS, we will get a prover optimal VSS scheme without trusted setup. And on the other hand, we also have an optimal VSS scheme with a trusted setup based on the KZG commitment. And that's all. Thank you. You can check our code via the GitHub link. And I'm happy to take the question session.